Hello and welcome, and today we're going to be taking a look at how we construct velocity diagrams, a graphical technique for solving engineering problems. Today we're going to be taking a look at a piston and crank, a very common engineering mechanism. When we're constructing velocity diagrams, we make use of what's called a space diagram. This is a simplified sketch that holds the main geometry we're going to use. So for example, here we have one link AB, which is the crank, and the other one BC, which is the connecting rod. We can see in this animation that as the crank rotates, the conrod pushes the piston up and down. The piston, of course, is constrained. It can only move in a straight up and down direction relative to A. Let's add some geometry to our model. So we now have the lengths of both links, 50 and 170 millimeters. And let's now consider what's happening. As AB rotates, the instantaneous velocity of B is at a right angle to the link AB. And we'll write this as VBA. And of course we use V equals R omega to work this out. Our piston movement, of course, is constrained. It can only move up and down. So, if we put it all together, then our velocity diagram has to be for a specific position. So in this case, we've chosen an angle of 25 degrees away from top dead center. That's what our velocity diagram is valid for. Okay, if you'd like to make a note now of the geometry, we're going to be using that to construct our velocity diagram. Our objective is to work out the velocity and direction of the piston. Okay, let's make a start on our velocity diagram. Let's start with a baseline. I've flipped my paper. It doesn't really matter. It just wanted to give myself a better scale. So there's my baseline and my first point A, which is on the crankshaft. Now, we need our angle, 25 degrees if you remember, so no substitute for using decent instruments and a decent scale. So let's get a construction line in 25 degrees away from our baseline, like that. And then I'm ready to draw in my first crank. So this gives me point A and point B. So get it labelled up, 25 degrees, 50 millimeters. Okay, now let's get our second line in, which is 170 millimeters up to the piston. So we can now label C. So that's completed our space diagram. This is our base geometry that gives us the directions for our vectors. Now, a little bit of calculation. Let's think about point B relative to A. Link AB is rotating, and we know 200 radians a second. So we need the instantaneous velocity of point B, and that's going to be perpendicular to the link AB. It can't be anywhere else. We write it as VBA, the velocity of B relative to A. And the way we work it out is simple. It's R times omega. So if we do the sum, and remember to write in meters, not millimeters, then we come out at 10 meters per second. So now let's get our first vector down in our velocity diagram. We're going to space it out. We don't have to join it up. We just need to use the directions. So I need a perpendicular to that link. I can put the vector pretty much anywhere on that line. So I'm going to come away from the geometry so I can see what's going on. And I'm going to use a decent scale. I'm going to use pretty much 1 to 1. So I'm going to use 1 centimeter is 1 meter per second. And I can drop my vector in there. So that's the velocity of B relative to A, 10 meters per second. Now when you're doing these, that's the direction, but it's A to B. It's a vector, so it's B relative to A, and it's drawn from A to B. Now we're going to pay attention to C, and we need it relative to B. And that's going to be perpendicular again. It has to be perpendicular to the link. So we know the direction it's perpendicular. And we can use that to drop a construction line in that's perpendicular to the link BC, and it has to go through the point B. Okay, so we know one end, we don't know where point C is yet, we just know it's on that line somewhere. So now we can come to the final point, which is C, and we can look at it relative to A. Now it's a piston, so we know it's constrained, it can move horizontally only. So we need to get a line that is parallel to AC and goes through point A. That has to be the direction of AC. There we go, there's a neat little way of getting a parallel line. Drop our construction line in, and the intersection becomes point C. So now we've got point C, we can simply scale from the diagram to work out what the velocities are. So C relative to B comes in at 9 meters per second, and then we can measure straight off AC to give us the velocity of the piston, which is what the question asked us, and you can see, I think, that it's 5.5 meters per second. So there we have a straightforward graphical technique for generating velocity diagrams.